So we have already seen 1, 2, and 5. And fortunately, we also know how does 3 and 4 work, right? We have seen how does 3 and 4 work because um, for the indefinite integrals, or I shouldn't say indefinite integral, I should say uh, derivatives, we have used these two properties, right? The idea is the same. That means if you find the definite integral of more than uh, one functions, more than one function, it will give you the same if you find the definite integral of those functions separately and then put it back into their respective places. That means if you're supposed to add those, then you can add those. If you are subtracting these, you can subtract this. So it will give you the same result. And we have used this in the derivatives as well, right? We did say it is the sum rule, right? So the idea is the same again. If you have, for example, this two functions could be anything, right? For example, I think we have seen examples of this the last time. Excuse me. I guess the function was, yeah, we can consider this one. So you have three different terms, right? We can consider this as three different functions. One function is 3x squared, the other one is 2x, the other one is 1. We can find, if we are trying to find the antiderivative, or I would say the definite integral on this occasion, what we can do is try and find the definite integral of these three separately, and then we can add this. It will give us the same result. And I think we have done the definite integral for this precise function, right? If I remember. Uh, anyway, so that's how we do it. And the constant function rule is, again, we have seen this in the derivative part. That means if you have a constant multiplied to a function, in other words, if you have a coefficient other than 1, I would say. If you have 1, it doesn't really matter. If you have any other coefficients, you can keep that outside and find the definite integral of whatever uh, is left. And if you multiply that constant to that definite integral, you'll still get the same result. Okay, this is what it means. And I think, as I said, the idea is exactly the same what we have done for the derivatives, right? Okay. Excuse me. Um, I know I can feel that my voice is not really clear today. So if you don't understand any of the words I'm trying to say, please let me know. Okay, don't hesitate. If you somehow don't understand any of the words, uh, let me know. I'll try to uh, say that again. Okay. All right. Before we move, um, okay. Before we move to the next slide, let me show you a really funny and interesting example. Yeah, this one. So if you are given a function like this, y equals, let's say square root of 1 minus x minus 3, the quantity squared. Okay. Now if I say, hey, can you find the shaded area for me? By shaded, I mean this. I know this is not really properly shaded, but I think you can differentiate it with the white background, but it should have used another color. Anyway, um, maybe they have used it so that it's accessible to everyone, right? Because not everyone is comfortable with some other color. So it's definitely important to make sure that everyone can understand what's going on here. So maybe that's the reason they have used this color. Anyway, so if I say, can you find the area of this shaded region? And the answer is actually pretty easy. It's not the case, although for all the functions and for all the graphs, and I'll not even ask you to uh, find it from the graph anyway. But I want to show you how to find this really easy. So if you have a function like this, you can actually feel that it looks like a square, right? Looks like a circle, right? We know the general formula of the circle, and it looks pretty similar. So if you square both sides, we'll get y squared equals to 1 minus x minus 3, the quantity squared, right? And if we change sides for this, because of this minus, if we take it to the left-hand side, it will become y squared plus x minus 3, the quantity squared, equals to 1. Do you agree? Just algebra, nothing else. I'm going to share the screen soon. I'm not really doing it for this one because I need some other slides to show. But does it make sense? I'm just doing some algebra. If we square both sides and then change sides for this, it will give you y squared plus x minus 3, the quantity squared, equals to 1. So y squared means y minus 0, the quantity squared, right? And we have x minus 3, the quantity squared. So definitely the center of the circle is 3, 0. That's what you can see, right? It's 3, 0. This is the circle. This is the x-axis. So definitely the y value is 0 on this line. So the circle has a center 3, 0. And on our right, we have 1, which is exactly the resemblance of r squared. 1 squared, 1 can be written as 1 squared. So that's r squared. That means our radius is 1. Do you agree? Radius is 1. And this shaded region is actually 1/4 of this entire circle. Do you agree? This function is actually the half circle. If it was negative square root of this item, then it would have been the other half. Anyway, we're not really bothered about that. This shaded region is 1/4 of the entire circle, if you can imagine the full circle here. Do you agree that it's actually 1/4? Because you have 4 equal parts here. Imagine the circle, right? Imagine the circle here on the bottom half of x-axis. So it's actually 1/4 of the entire circle. And we know the area of the circle is pi r squared. So what would be the area of this shaded region? Shouldn't it be 1/4 of pi r squared? And r is 1 here. So 1/4 of pi times 1 squared, which is pi over 4. Do you agree? Take your time. Don't really trust me in the first place. Take your time. You know the area of the circle. If you don't know, you have to know, because if you are progressing um, with some maths courses in future, um, you will definitely see some problems where you will need uh, different areas of different shapes, whether it be circular, um, rectangular, triangular. I think it's better if you know this beforehand. Okay, if you don't know, you should go over the formula again. There is no harm in uh, reviewing those stuffs, right? Okay, so now if I give you this particular function and say find the area, or if I say calculate the definite integral of this function from 3 to 4, you'll actually get the same result. Okay, but in some cases we can actually calculate it from the graph. It's really intuitive. If you use your intuitions, uh, we can actually solve problems like this. Okay, I'm just showing this funny example. If you don't understand it, uh, excuse me, try to express it as the uh, general formula of circle, and then just cross check your work. Okay, or you can let me know once we're done. All right, what's next? Okay, this one. All right, so this is just a general idea. If your function is positive, that means by positive I mean if it has positive values everywhere, or in other words, it doesn't matter what your x is, in return your f of x or your functional value is always non-negative, that means 0 or more, then if you're finding the area of that curve, that should still give you a non-negative area. Okay, the net area, of course. In general, the area can't be negative, but we consider negative area if it's below the x-axis. So what does it mean by net area? Net area means if you add or subtract, if you have anything below this x-axis, if you add and subtract all this, at the very end you'll still have something non-negative. Okay, that's what net area means. It's just a general idea you can remember. Does it make sense? Because I can show you, I think, yeah, let me show you one example. Yeah, like this one. So although, as I said, area can't be negative, but in maths we can have negative area. If you just consider the area above the x-axis positive, then the area below the x-axis is considered negative. Just to give us an idea, how does the curve is behaving, okay? Whether it has anything below the x-axis. So we need to differentiate this by that negative side. That negative side doesn't really mean that um, we have something negative. I mean, the area can't be negative, right? But it gives us an idea that it's decreasing for some reasons, right? Okay, so excuse me. So if I say net area, what I mean, you add 12 with 8, which is 20. And since we are saying that this is the negative area, you subtract it from the sum of these two. So 20 minus 10, the net area is actually 10, right? Net area is nothing but adding or subtracting all the areas. I should say adding all the areas. If you have something negative, then it actually falls into that category. So if you just add all these areas, you will get the net area. So plus 12 minus 10 plus 8. So the net area is 10. Does it make sense? Okay. Um, let's see what we have next. Yeah, I think we have uh, this. We have the idea of this, that if we are finding the area in between A to B, so this is literally, if we have any point C here, this is literally the area of this plus the area of this, right? We have seen this property before. Uh, I don't think that's a problem. Um, this is quite easy to understand. What else? So number 6 says the function is, if the function is integrable, and the definite integral is the sum of the areas of the region bounded by the graph of f and the x-axis. Okay, bounded by the graph of f and the x-axis. Right. So now what does it mean when this says bounded by x-axis? This is your x-axis, right? And your function or your graph is bounded by this x-axis all the time. Okay, if it's integrable, of course, it has to be integrable anyway. Okay. Okay, yeah, this is a good one. So if you have two functions and your first function is greater or equal than the other function, then the area under the same, I shouldn't say under, the area within the same interval uh, would be just behaving the same way. That means the area under this curve will be bigger than the area, at least greater or equal than the area under this curve. Okay, and you can clearly imagine why. If this function is greater or equal than this function, then all part of this graph is above or at least on level of this graph, right? Of the graph of this function. So if you find the area, it will clearly be more than what you have under this curve. You can clearly see this from the graph, in fact. The area under the function f of x would be all of this up to the x-axis, right? But for g, it's the slightly darker version, only this part. Remember, for f of x, it's not really this one, right? It's actually starting from here to the very end. This entire region will be the area for the first function, whereas for the second function, it's only the darker of these two. So it's obvious that if your function is greater or equal than the other one, then the area under that function will be greater or equal than the area of the other function. Okay, let's take a break for 30 seconds. Any question from this? Any quick question from the discussions we have had so far? No questions at all? Excuse- Okay, um, let's see what we have next. I think we're almost to the end of this slide, 5.2. Okay, this one, yeah. Although you will not really use this particular property here, I mean in Calc 1, but if you are moving to Calc 2 or some other maths course, for example, analysis, uh, I think you will use this several times, okay? Now what it means, um, if you can bound your function uh, within two values, let's say capital M and small m, then the area will also be bounded like this. Now, what does it mean? Let me show you the statement first. Yeah, this one, number 9. Okay. If you can bound your function like this, or that means if you can see two values, uh, which is creating this bound for your function, and if you're integrating or if you're trying to find the area of that function within a certain interval, let's say b and a, then this property will always hold. Okay, this one. This is a very, very important property. And as I said, if you uh, have any other maths course in future, I'm pretty sure you'll be using this one. This is really fun to work with, and this often makes our life easier. Okay, obviously we don't have enough time to uh, show the problems on this course, not because it's summer, um, maybe even in general terms. When I was TA for Calc 1 for 3 semesters in Reno, I I didn't see the instructor showing uh, this particular or using this particular property, because usually even in the general semester uh, we don't go this far, unfortunately, because it takes some time to build up towards it and then using as properties. So, but I'll try, because we have one more discussion tomorrow, uh, which will be a review session, by the way. But if you don't have too many questions, then I'll definitely show at least one example of this. Okay, this is going to be a really good property. And let me give you the reason behind this very quick. So this is your function. And if you draw a line like this, you can see this function could be bounded between this capital M and small m, right? That means these two parallel lines, this line and this line. This function could be bounded between these, right? So if that's the case, as I said, the area under this function, this curve, will be also bounded uh, by the area. Uh, I shouldn't say area, I think it's m times this length. Now, what is m? So the funny or interesting thing here, m is actually this length. Do you agree? M is this length, right? And b minus a is this length. So can you see this, that this is actually giving us an area, right? Although it doesn't look like an area, right? It doesn't look like an area, right? But it is It is actually an area because this m is a length, it's the height precisely, and this b minus a is another length. So if you can consider this smallish rectangle, this is the area of, I mean, m times b minus a, this length is actually the area of this smallish rectangle. And again, this capital M is this height, this length, right? Starting from here to this, or you can say starting from this 0, 0 to this. It's actually the same because everywhere on this line, your y is m, we know that. So if we consider m, this is the length of m, and of course b minus a is another length. So if you can consider this bigger rectangle, then m times b minus a is the area of that big rectangle, right? So clearly your area under this curve is bounded between these two rectangles. We can actually eyeball it, right? Okay, give me a second. All right, sorry about that. I know you're kind of, um, I don't know how to phrase this. I think I should rephrase this by irritated that I'm taking this awkward pauses every now and then. I apologize for this. All right, yeah, I think we're done with 5.2. This should be enough for your homework assignments as well. Okay. Um, let's move to 5.3. So 5.3, we have this precisely. 5.3 is all about the fundamental theorem of calculus. And we have two parts. We'll discuss it one by one. We'll see some graphs and try to understand why this is happening. Okay. All right. So the fundamental theorem, as I said, it has two parts. The first part says if your function is continuous on a certain interval, then the area is nothing but this. That means if you can uh, find uh, the definite integral, it will give you the area, right? And if it's, furthermore, if it's differentiable on that interval, initially we said it's continuous. We didn't say anything about the differentiability, but now we are saying that if it is differentiable on that interval, then if you find the derivative of the area function, it will in return give you the original function which we started to work on, which we had initially. And we actually know this, right? Because this is nothing but the antiderivative of the original function. So if you find the derivative of this, whatever you have, of this area function precisely, I would say, if you try to define it, then you should get the function in return, right? Because that's why we're saying this is the antiderivative. So this is nothing but the statement what we have done so far, okay? But we'll be using this uh, in future, so you should know how it actually works algebraically. We know the main idea, but the algebraic format of this is, let's say you have this uh, area function. So when I'm saying that you are finding the derivative of it, that means this is you're finding a prime of x, right? Or in other words, you are finding ddx of this function. Do you agree? That means you're taking ddx on both sides. You can, instead of a prime x, you can write ddx of ax, which is precisely a prime of x, right? So if we take ddx both sides, on both sides, that means if we find the derivative uh, in terms of x or with respect to x on both sides, then we get a prime of x on our left and the ddx of this thing, whatever we have, right? So this theorem says the ddx of this is precisely f of x. And you can actually cross-check it by taking any particular function, because this algebraic format often looks clumsy, often looks bizarre, right? But if we take a particular function and then do this numerically, it often looks more convincing. All right. Uh, I'll show examples of this, but first I want to go over the statements. Okay, so now the last part is saying that the area function of f is an antiderivative of f on that interval. Isn't it what we actually uh, know from the first instance of integrals or integration, right? That this function, this area function, is actually the antiderivative of this, right? We know this. This is the way we define it. This is what the statement is also trying to say. Okay. What's the second one? Okay. I'm scrolling to the wrong direction. Okay, the second part. Where have you seen this? The first question is, have you seen this before? Have you seen a format like this before? If yes, where? Again, we have seen this one um, in the previous lectures as well. Let me give you a hint. But having said that, can you recognize where have you seen this? Anyone?
It was the numerator of the equation for finding something. Can't remember what though.
Oh no, I can understand what you're trying to say. You are trying to say it's the numerator of finding the slope, right? Not really that. What I'm trying to say is you have actually seen this precise format, not this numerator uh, only. You have seen this precise format. Can you remember where have you seen this?
We used that yesterday to find the exact area under the curve.
Exactly. Very good. If you remember, when we found the definite integral of a certain function, what we did is, first of all, we found the antiderivative of this particular function. Then if you remember, we evaluated that antiderivative at these limits, and we plugged in the upper limit first and then subtracted the lower limit. Now can you remember? Right? Let me start sharing the screen now. I think we have seen enough slides. Now we can see some examples, and then you can practice in pairs or in groups later on. Okay, so I think we have this here. Let me see. Yeah, this one. This is exactly what the second part of the fundamental theorem of calculus says. And this is, sorry, let me show, yeah, this one. You can see this is the statement. This is your antiderivative, that is f, evaluated at b, evaluated at a. This is your b, this is your a. This is precisely what the statement was saying. Do you remember now? Can you recognize what I'm trying to say now? Okay, now, sorry, I'm looking for my pen to write on the iPad. Oh gosh, everything is so disorganized. Anyway, I can write it with my hand. All right, so let me give you examples now. So today is the last day of June 2021. All right, so the second statement, let me start with that, is saying if you're trying to find the area within this interval, this is nothing but finding the antiderivative. This, okay, I think this looks pretty similar, but it's actually the small f. Okay. And this is capital F, which is the general antiderivative of f. Okay, antiderivative of the small f. Okay, so this is actually the same as evaluating the antiderivative at the upper limit minus evaluating the antiderivative at the lower limit. Okay, let me show you one example. Yeah, we can try this. So y equals, let's say, 60x minus 6x squared. Okay, we can try to find the area of this function in the region 0 to 10, from 0 to 10. Okay, so this is what we're looking for, right? And obviously, our first job is to find the antiderivative, right? So what should you do first? What's the first thing you can do here? Anyone? What's the first thing you think we can do here?
Split it up into 60x and negative 6x squared.
I didn't understand. Will you please repeat it?
I was just saying split it up.
Oh, right. Yeah, split it up. Exactly. Sorry. I could not hear it in the first time. So obviously, we can first split it up into two parts like this, because we know it's the sum rule, right? So it would be from 0 to 10, negative, we have this negative, so 6x squared dx. Okay, now what's the antiderivative of 60x? Can you do that?
It'd be 60 times x squared over 2.
Very good. We can use the power rule, right? This is precisely x to the 1. 60x is, if we want to rewrite it for convenience, we can rewrite it like this: 60x to the 1. And if we use the power rule, obviously for using the constant function rule, we can keep the 60 outside. And using the power rule, it would give us x to the 1 plus 1 over 1 plus 1, right? The formula was, if you remember, let me write the formula for you again, was x to the n plus 1, oops, sorry, x to the n plus 1 over n plus 1, right? Minus, again, we can, oh, sorry, I think I forgot to write it. Yeah, you have to evaluate it at the limits, right? From 0, at 0 or and at 10. Okay, minus, again, we can keep this 60 outside. What's the antiderivative of x squared? Someone else? The antiderivative of x squared? No one?
X to the third over 3.
Exactly. This is the same rule. Using this particular rule, we can write x to the 2 plus 1 over 2 plus 1. And again, we need to evaluate this at the limits. So if we can simplify it just a little bit, this 60 and 2 will give us 30. And this x squared, again, we're evaluating this on at these points, right? So we'll just replace x by this precise value. Sorry. We'll just replace x by these precise values. So it will be first 10 squared minus the lower limit, which is 0, 0 squared. So this is nothing but finding the antiderivative. This is the antiderivative, f of x. Oh my God. Yeah. Antiderivative, and we're just evaluating this like it. So f of b minus f of a. This is what we have done here, right? And this is exactly what the statement said. Okay. Now, let's keep doing it. So this 3 and 6 will give us a -2. And again, we'll be evaluating this function x cubed at these points. So we'll start with the upper limit, 10 cubed, minus the lower limit, 0 cubed. Okay. So 100 squared, so 10 squared is 100. So let me do it one by one. 10 squared is 100. And 100 minus 0 is 100. So this will be 30 times 100 minus 10 cubed is 1,000. Minus 0 is always going to be the same. So it will be 1,000. So 2 times 1,000. So precisely we'll have 3,000 minus 2,000, which is 1,000. This should be the area of this particular function. Any question from this? Any question? Doesn't matter. Oh, I think something in the chat. Let me see. I have a doctor's appointment. I'll be leaving. Okay. Oh, I think you have already left. Anyway, no problem. Yeah. All right, so any question from the calculation? Because you will be doing this for the smallish part of this last couple of days of the semester, for the smallish part of the semester, right? Smallest last couple of days. No questions at all? Okay, so let's take a break, and when we come back, we'll be practicing a couple of more of this. Okay, so let's meet at 10:10. Okay, see you in 5 minutes.
Negative. Go for it.
Yeah, Matthew, go for it.
I was just going to say -3 sine of 3x.
Very good, exactly. So it was, not it was, it is -3 sine 3x, right? What it means, if it was the derivative, the coefficient would have come in front, right? Or if I generalize this, d dx of any cosine or sine or any I think precisely I should say any trigonometric function, if we have a coefficient m with the x for the angle precisely, then this m comes in front like this, right? This m, obviously this negative is because it's coming from cosine. There may not be negative for some other functions. That's not the case. The case is this m comes in front, right? If we have any coefficient in the angle, then it comes in front like this. This m, this is m, by the way. Let me write it clearly if I can. M, right? This m comes in front. So if I find the antiderivative of this, what would have happened? So let me start with this one. Can you see that this is exactly the same as this? Do you agree if I say that? Do you agree? No one agrees? Really? Okay, so your silence, I think I would take that as the agreement. That means you're actually fine with what I'm saying, right? Okay, so this part, you can see the red circle part is exactly the same problem we have. So now if I use the fundamental theorem of calculus, don't I know that the antiderivative of this should be this? Would it be wrong if I say that? I know that, right? I have seen this statement just a couple of minutes back before the break. So let me write it for you. I know the TDX of cosine 3x is -3 sine 3x. That means if I do the other way around, so the sine, well, let me try this way. So the -3 sine 3x, the antiderivative of it would be cosine 3x. right? I can use the fundamental theorem of calculus. The antiderivative of this should give me this in return. And if I do some really quick algebra here to simplify it, oh, I think I should write a dx here. Sorry about that. If I do just a little bit of simplification, it becomes this. Do you agree? Anyone? Any question? I'm just doing algebra here. Obviously, I have used the fundamental theorem of calculus, but I haven't really done any precise antiderivative here. I haven't really calculated it. Okay, I'm just generating it by using that fundamental theorem and just a little bit of algebra. Does it make sense? Again, you don't need to do this for any problem, okay? I'm just trying to build up towards the formula. I'm trying to build up a formula, nothing else. You don't need to do like this. Soon you will see I'll generalize this and give you a formula, and you can use that formula straight away when you have a problem like this. But before that, do you agree what I have done here? Does it make sense?
Yeah.
So I assume it makes sense to everyone. If it doesn't, uh, please let me know, okay? Because we are almost to the end. And obviously, I want to convince at least most of you, if not everyone. Okay. All right. Now, if I generalize this particular calculation, would it be wrong if I say that if you have any function of this format, okay, this will actually, this negative sign is again because of the sine function. This may or may not be for the other trigonometric functions. We know the general formula of sine x, right? The antiderivative of sine x is negative cosine x. So you can consider this negative of, the part of that formula. It's not really the generalization of this problem. The generalization of this problem is if I say, if you have a problem like this, then, for the derivative, the coefficient came in front like this, but now it will be the reciprocal of that. 1 over m cosine mx. So this is the general format of antiderivatives. So for derivatives, the coefficient comes in front. For antiderivative, the reciprocal of that coefficient comes in front. That means 1 over that coefficient will be here. Okay? This is the generalization of it. So now if I use this generalization and find, let's say from 0 to pi, since we have done it for 3x, let us try for some other function. Let's say 5x dx. What would be the answer? Obviously, for sine function, we'll have negative 1 over m, that means 1 over 5 cosine of 5x, and we're not yet done. Since it's a definite integral, we need to evaluate this at the limit points, upper and lower limits. This is a 0, by the way. Any question from this? just using this formula, nothing else. And obviously for evaluation part, it's the same. You just I'll do that, I'll show that, but any question from this part? No questions at all? Okay, let's try to evaluate this now. So it would be -1/5 for cosine 5x. Again, evaluation part, let me give you a gentle reminder. You just need to replace your x by the value you have in place of that upper and lower limit, right? So it would be cosine, I assume I'll need more space, so I think I should start from here. So -1/5 cosine of 5 pi, right? This is the upper limit, minus cosine of 0. This is the lower limit. Do you agree? Okay, now we just need to know the values of these cosine functions, and that's it. What's cosine 5 pi? Anyone? You can use your calculator, you can use the unit circle, however you want to find it. It should be fine. Okay.
Should be -5, right?
-5. It can't be -5, that's for sure, because your sine or cosine function always gives you a value within this. It doesn't exceed -1 or 1. It actually lies between this.
Oh, I did it as 5 cosine of pi.
Okay, yeah. 5 cosine of pi can be 5, that's for sure, or,
Yeah.
or that is a possibility, but it's cosine 5 instead. Yeah.
Yeah.
So you can use your calculator, or you can use the unit circle uh, if you're confident enough that you actually know this, uh, know this how to use this properly. Then I think you can uh, use the unit circle, the idea of unit circle. So I know the value precisely, so I can straight away plug it in, which is -1 for 5 pi. For any uh, odd pi, it would be -1. So it's -1 minus, what's cosine 0?
1.
1. Very good. So it's 1. Now, if I simplify it further, it would be -2, right? Here, this part would be -2, because -1 and -1 would give us -2. And if I multiply this by this negative, it would be positive. So it's positive 2/5. Just algebra, nothing else. I'm not doing any calculus here. The calculus part was done here. This is sheer trigonometry, and this is exactly algebra. Any question from this? Take your time, okay? You don't need to be in a hurry. Any question? No question at all? Okay. Excuse me. Let me show you another example. And of course, then I'll give you problems for practice. Yeah, I think I can try this one. Let's try from 0 to natural log of 2. Let us try e to the negative 4x. Okay. All right, so the first question would be, what's the derivative of e to the x? I should say antiderivative of e to the x. Anyone? The antiderivative? What's the antiderivative of e to the x?
The e to the x plus c.
Do you mean this?
Yeah.
You don't need to add c though, because we are talking about definite
yeah.
integral. Yeah, I understand why you said that. Yeah, that makes sense. But yeah, when you're trying to find the definite integral, if you add that c, you might get penalized. Okay, just remember, you add this c for indefinite integral, it actually works both ways. If you don't add this c for the indefinite integral, you'll get penalized. If you add this c for definite integral, you'll also get penalized. So you just need to be careful about it. I'm not saying this for this problem. It's in general, right? And it's for everyone. So yeah, you're right. So the antiderivative of e to the x is e to the x. You're spot on. But it's not exactly e to the x. We have something more, right? What can we do? What should we do? That means we have this e to the mx. Can anyone guess what would be the case? I've already gave you a hint. I have given you a hint. Anyone? Any guess? No guess at all? So I know for e to the x, it would be e to the x. If we have anything else, the general idea is it will have like this, right? This is the hint I was talking about. This is for any coefficient, because if you remember, for derivatives, any m assigned to that x, any coefficients actually comes in front. So for antiderivatives, the reciprocal will come in front. Okay. For the derivative, the coefficient itself comes in front. And for the antiderivative, it's not exactly the coefficient, it's actually the reciprocal of that coefficient. So if we use that, what's the antiderivative of e to the negative 4x? Anyone?
Negative 1/4 e to the negative 4x.
Very good.
And you have to put the bar in evaluating.
Very good, exactly. So since we have a -4, our m is -4 here, so we should expect a -1/4, right? And e to the -4x will be the same. And of course, we need to evaluate this at 0 and natural log of 2. Okay, any question up to this? We're not yet done, by the way. We need to see and excuse me, evaluate it at these two values. But before that, any question from this? No questions at all? All good? Okay. So -1/4 e to the -4 will, remember, we'll just replace our x, nothing else. Everything else remains the same. So in place of x, I'll have a natural log of 2 minus e to the -4. In place of x, I'll have the 0. And of course, we need to evaluate this now. Or I should say, we need to find the value of this. Okay. So what's the value of e to the -4 natural log of 2? Anyone? I have used my calculator. It's actually 0.0625. Okay. And what's e to the 0? 1, right? We know e to the 0 is 1. So if we find the value, finally it would be 0.2343, or I think I can write 44. This would be the answer. I'm just doing algebra, nothing else. This is
I have a question. If
Yeah.
they ask for an exact number for the answer, should we keep it a fraction or answer it in a decimal?
Okay. So what do you mean by exact? I mean, this could go on forever, right? I have just taken this up to 4 decimals. It actually doesn't end here. Do you mean, I mean, exact by, you mean the format?
Yeah, if they say like answer like an exact number, if we would keep it as the 15/64, would that be more of an exact, or is the decimal okay? I don't know if I'm making sense.
Yeah, I understand your question. I don't think any of this format would be a problem. Uh, well, the Pearson has its own um, tolerance level. That
Yeah, usually in Pearson, they want the fraction.
Okay, good to know.
Otherwise, it'll say use a decimal to this many places.
Okay, so yeah, it could be the case. By default, they might want the fraction, but I don't think it's a problem. If you feel that you have done it right, but just because you have provided a decimal instead of a fraction, you have got it wrong. I mean, they have penalized you. Let me know. I'll give you full credit, because mathematically there is no harm in doing this. There is no harm in keeping this in decimals. There is no obligation to keep it in fractions. If it's the by default settings of Pearson, we can take care of it. Okay, just let me know if it's the case. I don't think that should be, but anyway, let me know. Okay. All right. Any other questions from this? No questions at all? Okay. Now I'll give you a couple of problems so that you can practice now. All right, so which one should I give? Oh, I think before that, let me show you one more really interesting example, and then I'll give you problems to practice on. Okay, so let's say my temperature, I mean not my temperature, let's say the room temperature is increasing at the rate 12e to the negative, what time card, please send a screenshot. Okay, I can see that later. T to the or e to the t over 10, and obviously it's the rate, so it would be degrees Celsius over minute. It's not in Fahrenheit, it's in degrees Celsius. So that's the rate it's changing, or it's increasing precisely, 12e to the negative t over 10. We need to find the change in the temperature within this interval. That means from right from the word go to the 15th minute, we want to find the change in the temperature. What should we do? Just because we are doing antiderivatives now, you will say that we should find the antiderivative. Yeah, that's true. We'll be finding the antiderivative of this. But what's the reason behind it? Why should we calculate the antiderivative? It makes sense if I say that I'll be finding the antiderivative, but what could be the reason behind it? Remember, we're trying to find the change in the temperature within this interval. This is time interval, by the way, in minutes. So clearly we'll be finding antiderivatives, but the question is why? Why do you think we should be finding the antiderivative? Anyone? Give it a try. No one at all? Okay, so the first thing we need, or comes into your mind, that we're looking for the temperature, right? Is this the temperature? Is it?
That would be the rate of change of the temperature.
So if this is the rate of change, isn't it this?
Yes.
Okay. What we are looking for is this t, not ddt of t. We're looking for this capital T, the temperature, not the rate. Now can you feel why should you do the antiderivative of it? Anyone? That is, if we find the antiderivative of this, if you remember the fundamental theorem of calculus part 1, we have seen this, right? This should be in terms of t, right here. So this would precisely give us the t. Don't you agree with that?
That makes sense.
Right? Because this is the derivative. If I can find the antiderivative of it, it should give me the t, the temperature I'm looking for. That's why we'll be doing this antiderivative, not just because we are in the chapter antiderivative. It has to make sense, right? Why should we go for antiderivative? If you see a question straight away, if you see a question like this straight away, it should your intuition should say, hey, you must be looking for the antiderivative. Okay, now let's try and find that. So we're looking for, instead I think I can plug in the function itself, which is 12 e to the negative t over 10. And of course, we'll want to find it from 0 to 15. Okay. We can keep the 12 outside. What's the derivative? It would be a tricky one. What's the antiderivative, I would say, of e to the negative t over 10? Be careful, it's a fraction, but you can use, okay, let me wait for your answer. What should we do? What's the antiderivative of e to the negative t over 10? Anyone? Give it a try. No one at all? What if I rewrite this as negative 1 over 10 times t? Now can you do it? This is exactly the same, right? Negative t over 10 is exactly the same as negative 1 over 10 times t.
So it would become negative 10 e to the t.
Very good, yeah. This is my m, right? So the reciprocal of that m will come in front. The reciprocal of negative 1 over 10 is negative 10. If you have 10, the reciprocal of it is 1 over 10, and it's vice versa. If you have 1 over 10, the reciprocal of that is 10, right? You just flip it, nothing else. Okay. And of course, it will be the same here, negative t over 10. And you need to evaluate this at these points. Again, any question before we do the evaluation part? Any question? No question at all? Okay, so this would be negative 120 e to the 15 over 10 minus e to the 0. And if you use your calculator, you'll get a 93.22. And of course, it's in degrees Celsius because our unit for the rate of change was in degrees Celsius, right? So clearly, the temperature will be in degrees Celsius. Any question from this? No question at all?
What did you get for e to the 15 over 10? I did the calculation. I got a really weird number.
What did you get?
I got I did it as e to the 1.5, and I got 4.48.
Oh, sorry. I think I've just missed out the negative in front. Sorry about that. Yeah, you can see there is a negative in front.
Gotcha.
Yeah, you're right. Yeah,
Okay, thank you.
thank you for that. Yeah, definitely you have that negative. Okay, any other questions? Any other questions? I know if you start doing this, you might encounter some more problems, right? You might see some questions. But can you remember? Can you see any questions right now? Okay, now, as I said, I think, yeah, we have enough time. Let me give you a problem so that you can practice. Because I don't think we have enough time to, uh, excuse me, to go for the next uh, slide, right? Okay, yeah, this would be a good one. Find the area in pi over 4 to 5 pi over 4 of this function sin x minus cosine x dx. Okay, try this one. I'll not create a breakout room now, or should I? Yeah, I think I can create a breakout room real quick.
Find the
Separate.
derivatives.
You can go.
Sorry. Just find the antiderivatives or separate it like Simona said.
Okay, so let's separate it first. Sin x dx minus the other part of the function cosine x dx, right? What's the antiderivatives now? Someone from group 1. Antiderivative of sin x.
It should be negative cosine x minus sine x.
No, do it one by one. Let's do it one.
Oh,
What's the
sorry.
derivative of sin x?
Negative cosine x.
Negative cosine x, and we need to evaluate this here. And what's the derivative of cosine x? Someone from the second group?
Negative sin x.
No, the antiderivative of cosine x is not negative sin x.
Sin x?
Yeah, do you mean including this negative? Yeah, including this, it's negative sin x. That's true.
Yeah, I was including it.
Okay. But my question was the antiderivative of cosine x. Anyway, yeah, all right. So it's pi over 4, 5 pi over 4. Okay, if we evaluate this, let's keep the negative outside. Cosine 5 pi over 4. Can anyone from the first group tell me what's the value of cosine 5 pi over 4? Minus cosine pi over 4. From the first group, anyone? And sine 5 pi over 4 minus sine pi over 4. Okay.
Cosine of 5 pi over 4 is negative root 2 over 2.
Oops, sorry. And what's cosine pi over 4?
Root 2 over 2.
What's sine pi over 4?
It's the same thing, negative root 2 over 2.
Okay, so what should be the final answer then? Is this what you have got as well?
Yes.
Can someone from each group confirm that this is the exact solution you also have? If you don't have this one, I assume you have done it wrong somewhere, maybe in the calculation, I mean the trigonometric value, maybe in the algebra, it could be in the antiderivative part as well, but it has to be 2 square root of 2. Okay.
I have a question.
Yeah.
So I've been finding the full antiderivative and then evaluating.
Yeah, it should give you the same result. We know that
Okay.
using the
Then
sum rule.
I did it wrong.
Yeah. All right. So let's meet tomorrow for one last time. And if you have any question, don't hesitate to send me emails. Okay. I'll see you tomorrow.
Thank you.
Thank you.